Hello, welcome back to the second course in physics. We are still discussing the magnetic fields produced by currents and their effects. This is still the topics of magnetostatics, and we are dealing with the sources of the magnetic fields, and we are discussing the magnetic fields produced by currents, the part 2 of this topic in this lecture. And this lecture will contain a quick introduction, and then we will derive Ampere's law, which is the law we use to determine the magnetic field of current-carrying conductors with special symmetries. And then we will use this Ampere's law to evaluate the magnetic field produced by currents in special cases. We will, for example, calculate the magnetic induction outside a long straight wire, and we will also evaluate the magnetic induction inside a long straight wire using Ampere's law. We will also encounter the problem of the force of interaction between two parallel wires carrying currents. And then we will derive the differential form or the local form of Ampere's law. And then we will introduce a new concept, which is the vector potential, and we will derive the magnetic flux in terms of that, and we will discuss the gauge invariance of the magnetic fields. So to begin with, we have to recall that the evaluation of the magnetic fields for current distributions using Biot-Savart law could be tedious in special cases, could be difficult because it requires evaluation of an integral, and that could be difficult somehow. So there are some cases where we can apply certain special symmetries of a problem to simplify the problem of evaluation of magnetic field. And in this context, André Marie Ampere, who lived in the period 1775 to 1836, has provided an alternative method for calculating the magnetic field in special cases. Ampere's law applies to problems with special symmetries only. It cannot be applied, we have to emphasize, it cannot be applied to all problems, only problems with special symmetries, specifically if we can find a contour, a simple contour over which we can do an integral, and if the magnetic field induction is constant, the value of the magnetic field is constant along that contour, then Ampere's law becomes significantly important and simple in calculating the magnetic field, the magnitude of the magnetic field. And then the direction of the magnetic field can be deduced from the right-hand rule at any point in space. So now we derive Ampere's law from basic principles, and we consider that we have a conductor carrying current I, and we draw a loop C, a closed loop, an Amperian path called. This is called an Amperian path or Amperian loop around the conductor. So the conductor is enclosed within that loop. And now what we do is we take an element of the current, DL2, which is an element of the conductor, and we evaluate the magnetic field produced by that element of current at the position DL1 of the Amperian loop. The position of the element DL1 of the Amperian loop is R with respect to DL2. And so if we take the magnetic field B produced by the current dot DL1, which is the element on the Amperian loop, and we evaluate this magnitude B dot DL1 over all the Amperian loop, what do we have? We just here substitute for the amount of B, because we know the amount of B, we can calculate it by using Biot-Savart law. So this is equal to mu naught I over 4 pi times the integral over L. L is the wire or the conductor that carries the current. So we integrate over the current carrying conductor, DL2 cross R over R cube evaluated over DL2 over L, the current carrying conductor, times mu naught I over 4 pi. That gives the magnetic field B of the current carrying conductor at the location of DL1. And now this quantity, we dot it with DL1 as it is here in the left-hand side of the equation, and we integrate over C, which is the Amperian loop. So B dot DL integrated over the Amperian loop, B dot DL1 integrated over the Amperian loop, C, is equal to this quantity. Now we will rearrange this quantity. The quantity in the integral is simply the solid angle corresponding to the surface area that is made up by the two elements of length, which is DL1 on the current carrying conductor, DL2, and DL1 on the Amperian loop. So DL1 and DL2 as two elements of length cross together, DL1 cross DL2 or DL2 cross DL1 gives the area that is made by this. And if we rearrange the integrand, the quantity in the integral, we notice that DL2 cross R over R cube dot DL1 is simply equals to R dot DL1 cross DL2 over R cube. This is an identity. And DL1 cross DL2 is simply the area that is made by DL1 and DL2 by the two elements of the Amperian loop and of the wire carrying the current. And that area has, of course, it's a vector quantity dotted with R dot R. It gives us the cosine theta between the normal to this area and the position vector times R, the position vector, over R cube. It gives 1 over R square. So this gives simply DL1 magnitude, DL2 magnitude times cosine theta over R square. And this is simply the solid angle subtended by the element of area that is made by DL1 cross DL2, d omega. That's d omega. And now if we integrate this quantity over all space, this d omega, because we are integrating over the whole loop, C, and we are integrating over the whole current carrying conductor. If we integrate this all over all space, the integration of d omega over all space is equal to 4 pi, simply. So that gives us the result that the integral of B introduced by the current carrying conductor dot dl integrated over an Amperian closed loop surrounding the current is equal to mu naught times I inside the loop, that is enclosed by the loop, divided by 4 pi times 4 pi, which is simply mu naught I enclosed. So this is Ampere's law, and this states that the current that contributes to this integral is only the current that is encircled inside the Amperian path only. So if we have an Amperian path and we evaluate B dot dl around this path, the only currents that make contribution are only the currents that are inside this Amperian path, the enclosed I sub ENC, the enclosed currents only. And now let's use this law, Ampere's law, to evaluate the magnetic field due to currents in special cases. Notice that the magnetic induction, for example, outside a long straight wire is constant at all locations around the wire at the same distance. So if we draw a given circle around the wire where the wire is the axis of that circle, the magnetic field at all points on that path has the same magnitude. So in that case, we can use an Amperian path around a long straight wire carrying a current. We can use Ampere's law, and outside the current, B dot dl integrated over the Amperian path. The Amperian path is C here. It's a circle around the wire. This is simply a cross-section of the wire with radius capital R, and small r is the radius of the Amperian path. So B dot dl is equal to mu naught I enclosed within the Amperian path, and in this case, the current enclosed within the Amperian path is the total current carried by the conductor, I. So I enclosed is simply I. And, and since B is constant, because B depends on how far you are from the conductor, from the current source, and since all the points on the path are at the same distance from the center of the wire, then the magnetic field has a constant magnitude at all points. That means this integral has a constant, this magnetic induction has a constant magnitude, and the direction is in the direction of the path. As we have mentioned before, the magnetic field has a direction that goes around the current carrying wire that goes with the direction of the fingers of the right hand if we point the thumb towards the in the direction of the current. So B and DL are in the same direction. The angle between them is 0, and cosine 0 is 1. So the integral is simply B times integral over the Amperian path of dl. The integral of over the Amperian path of dl is simply L, the total length of the Amperian path, which is 2 pi r. So that gives us the result. B times 2 pi r is equal to mu naught I, or the magnetic induction at a point, a distance r from the center of the wire, is equal to mu naught I over 2 pi r. This is exactly the same result that we obtained by applying directly Biot-Savart law. And it should be the same, but it's much easier. If we notice, the calculation is much, much easier than using Biot-Savart law. Another example is if we want to calculate the magnetic field inside a long wire, a straight wire. Here, Ampere's law can be very useful because it's very difficult to use Biot-Savart's law to evaluate the magnetic field inside the conducting wire. And in this case, we take an Amperian path at the location where we are interested in calculating the magnetic field. So let's assume that we are taking the Amperian path C with a radius small r inside the wire. And now here we apply Ampere's law. B dot dl integrated over the Amperian path is equal to mu naught I enclosed within C. That's not all the current I. It's different from the previous case. In this case, B times the Amperian length, which is 2 pi times r, is equal to mu naught times the enclosed part of the current. The enclosed part of the current can be determined by, if we consider that the current is uniform, has a uniform density, then we take the total current I divided by pi capital R square. That gives us the current density. And we multiply it by the area of the Amperian loop, pi small r square. That gives the enclosed current within the Amperian loop. And this gives B is equal to mu naught I over 2 pi capital R squared. This is a constant, times r, which is the distance from the center of the wire. So this tells us that the magnetic field is proportional, linearly proportional to the distance from the center, because as we move away from the distance of the center, as far as we are inside the conductor, we are increasing the current that is enclosed within the loop, and increasing the current will increase the magnetic induction at these points until, of course, we reach the end of the wire, until we reach the outer surface of the wire. After that, the magnetic field starts dropping as 1 over r. So a plot of this will be like this. Inside the wire, until from small r equals 0 up to the radius of the wire itself, the magnetic induction is increasing linearly with r, and then after that, outside the wire, it is decreasing monotonically as 1 over r. So this illustrates how simple it is to use Ampere's law in calculating the magnetic induction in these cases, in these symmetrical cases. And now we encounter the problem of forces between two parallel wires. We have mentioned that two currents exert forces on each other. And for simplicity, because we have calculated the magnetic field due to one wire, straight wire, long straight wire carrying current, because we do that, we can consider the problem of forces between two long parallel wires carrying currents. Now, experimentally, it has been seen that the parallel currents, if the currents are flowing in the same direction in the parallel wires, parallel currents, such parallel currents, they attract each other. So the forces, as shown here in this figure, the force acting on one wire is directed towards the second wire. Anti-parallel currents, if we just flip one of the directions of the currents, because the force or the magnetic field and consequently the force is dependent on the direction of the current, then if we just flip one current direction, then the force will flip in direction, and then the forces will be repellent forces. For anti-parallel currents, the forces the currents repel each other. And now, if we consider the force that for example, wire A, which is an infinite wire, a long straight wire carrying current IA, if we consider the force that this current exerts on a given section of length L, for example, of wire B. What is that? Now, previously we have found that a long straight wire produces a magnetic field at a distance from it. Suppose that we are calculating the magnetic field due to wire A at a distance d from wire A, because at a distance d lies wire B. So in order to calculate the force, we have to calculate the magnetic field due to A at a distance d from it. So that is equal to mu naught times IA, the current, divided by 2 pi times the distance d to that point of interest. So this is the magnetic field, and if we consider that the force exerted on a current, on a straight wire carrying current, if the straight wire is of length L, is equal to I times L cross B. And thus, I is the IB, the current of the second wire, it's IB, times L is the length of that wire, of the section of wire B, times B, the magnetic field applied in that region of the wire, which is mu naught IA over 2 pi d, which is the magnetic field due to the current I in wire A. So this is the magnitude of the force, and simply L cross B is simply L magnitude times B magnitude, because this wire A would produce a magnetic field that is going into the plane, which is perpendicular to the current in wire B. So the magnetic field produced by A is perpendicular to the wire, to the current in wire B. So that means L cross B is simply L magnitude times B magnitude, and the force would be in an attractive direction using the right hand rule. And this is the magnitude of the force. Now we consider the differential form of Ampere's law. So far we have discussed the integral form of Ampere's law, and now we can find the local form or the differential form that applies locally in space. And that can be done as follows. If we consider a path C, and that path enclosed an area in space, which is S, surface area S, we take a small element of that area, ds, and we keep in mind that this element of area has direction as well as magnitude. And now we use Stokes' law applied to this integral, which is the integral that appears in Ampere's law. B dot dl integrated over the Amperian path C using Stokes' law is converted into an integral over the surface area enclosed within the Amperian path of curl B dot ds. So curl B at this point times dot product with the element of the surface at that point integrated over all the surface will give B dot dl integrated over the Amperian path surrounding that surface area. And now, if we use Ampere's law and recall that B dot dl integrated over C is simply mu naught I, and we remember that I is the current enclosed inside the Amperian path. So we go to the spots where I is flowing inside the Amperian path, and we replace I, the current, by the integral J dot ds. So we assume that there is a current density J flowing in that element of area ds. So J dot ds is the current flowing in that area ds, and if we integrate over all the area enclosed within the Amperian path, that gives us J dot ds, which is the total current enclosed within the Amperian path, times mu naught. That gives us B dot dl. So comparing these two, this is, the first is curl B dot ds integrated over S. The second is mu naught J dot ds integrated over S. So this gives us the result that curl B minus J integrated over minus mu naught J integrated over ds is equal to 0. The solution is simply curl B is equal to mu naught J. This is the same. This is actually Ampere's law. This is what we have done. We just modified Ampere's law to be presented in a differential form rather than in integral form. So this curl B is equal to mu naught J is Ampere's law, but in differential form. We will be needing this this formula in the future when we talk about Maxwell's equations. And now we introduce a new concept which is related to the magnetic field strength. We introduce the concept of the vector potential. And we recall our knowledge so far in physics and math. And we recall that it can be shown that for any vector, the divergence of its curl is equal to 0 if we take any vector in space. And we take the curl of that vector, then we take the divergence of the result. This is equal to 0. So consider that we have a vector A, which is a general vector in space. The curl of that vector is a given quantity. The divergence of that curl is equal to 0. This is a general result of calculation. And we recall the divergence of the magnetic induction div B is equal to 0. Since this is true, because we don't have magnetic monopoles in space, and also we have the divergence of the curl of a vector is equal to 0. That means B in general is a curl of a vector. It should be a curl in the form of a curl of a vector. And thus, we replace B by curl A, and we say that curl A is equal to B. Thus, the magnetic induction can be written in terms of a vector potential, which we call A, and we can write in general B is equal to curl A. This is a correct statement. Now, this could give, for a special choice of A, it gives the magnetic induction in space. Now, let's look into the magnetic flux in terms of that, in terms of the vector potential. The magnetic flux through a surface, consider this is the surface bound by a contour C, and we have magnetic induction lines, magnetic field lines crossing that surface area. Of course, since the surface is not closed, it's open, then the flux is not necessarily 0 across that surface. It's only the total flux across a closed surface is equal to 0. We must remember that. And the flux across this surface, which is not closed, is simply the integral over the surface of B dot ds. So we go B dot ds, calculating the flux through every element of this surface, and we sum over all the surface, and that is the flux through that surface area S, which is enclosed within the contour C. And now we use Stokes' law, Stokes' theorem, to convert the integral over a surface area into first of all, we substitute for B, the magnetic induction, in terms of the vector potential. B is curl A. So this integral over the surface area is simply the integral over the surface area of curl A dot ds. And now we use Stokes' law, Stokes' theorem, to convert the integral over the surface area into a contour integration, into an integral around the contour surrounding that surface area. Curl A dot ds is simply equals to the contour integration of A dot dl itself. And that is phi. So the flux is simply A dot dl integrated around the contour. And now let's remember that the way we define the magnetic induction, that it calls for some sort of a gauge invariance of the field. That is, the field is invariant under some sort of transformation. If we recall that the curl of the gradient of any scalar function is 0, the curl of any scalar function, the curl of the gradient of any scalar function is 0, and the magnetic induction, thus we would arrive at a conclusion that the magnetic induction would remain constant under the gauge transformation, the following gauge transformation, if we replace the vector potential A by A prime, where A prime is simply equals to the vector potential A plus the gradient of a scalar function, gradient f. This transformation leaves the magnetic induction unchanged. What we care about is the magnetic induction. That is the strength of the magnetic field in space that we are considering. A is a mathematical formulation only, and to calculate the magnetic induction. So if we make that transformation, A prime going to A plus gradient of a scalar function, the curl of A prime is equal to the curl of A plus the curl of the gradient of f. The curl of the gradient of f is 0. That means the curl of A prime is equal to the curl of A. That means the magnetic induction calculated from A prime is exactly the same as the magnetic induction calculated from A. And we call that gauge invariance, that the magnetic induction remains the same under that transformation of fields. And now we consider the Coulomb gauge, the Coulomb transformation gauge, and we recall in this context that it can be shown in the future. We will show when we come to the dynamical effects that the divergence of the vector potential is proportional to the time derivative of the electric potential. Since that is true, then in the steady state, where we have no time dependence of the potentials, then the time derivative of the electric potential is 0, which means the divergence of the vector potential is 0. So the divergence of the vector potential div A is equal to 0. This is called Coulomb gauge, which is applicable in steady state because we have no dynamical effects, we have no time dependence of fields on time. And now notice that the curl of the magnetic induction, curl B, is simply equals to curl of B in terms of the vector potential, which is curl A. So it's curl A, grad cross gradient cross A. And that is equal by definition to mu naught J. This is Ampere's law in local form or in differential form. We just substitute for B in terms of the vector potential. And now we expand this quantity, grad cross A, by using standard algebra. This quantity, grad cross A, curl A, is equal to gradient of div A minus gradient squared A. This is this quantity, and now we substitute for this result in the above formula, and we get in the steady state div A is equal to 0, which is the Coulomb gauge, as we have mentioned a little while ago. Then we arrive at the result, gradient squared of the vector potential A is equal to mu naught to minus mu naught J, which is the current density. This is an equation, this is a relation which is similar to the Poisson equation for the electrostatic potential. The difference is that this is a vector equation. It's a vector differential equation that has, in general, 3 components in space. So we have Poisson equation in 3 components. We have some sort of 3 equations, and it looks very similar to the Poisson equation in the electrostatic case. Now we have defined the vector potential and the relation of the vector potential with the magnetic induction, and now we consider the integral form of the vector potential. Now recall the definition of the magnetic induction, but instead of writing it in terms of the current I dl, we write it in terms of the current density J d tau, which is the volume element through which the current is flowing. So B is mu naught over 4 pi times the integral over the volume where the current is flowing times the current density J cross R. R is the location of the point of interest where we are calculating the field, over R cube integrated over the volume where the current is flowing, integrated over the source of the current, actually. So this is the magnetic induction. And this is simply equal to mu naught over 4 pi, and considering that, just rearranging this quantity and rewriting R vector over R cube as minus the gradient of 1 over R, then the result is simply B is equal to mu naught over 4 pi times the integral over the source of the current times the gradient of 1 over R cross J, the current density, integrated over the source of the current. Also, we have the gradient of 1 over R. Now we are trying to simplify this result. The gradient of 1 over R cross J is simply equals to the gradient to the curl of J over R, or grad cross J over R, minus 1 over R times the curl of J. This is an identity, just it's like applying the derivative to two different variables, and this is simply equals to grad cross J over R, or curl J over R. This is true because the gradient here is a differential operator that includes coordinates that are different from the coordinates of the volume of the source where the current is flowing. So the coordinates of J are different from the coordinates of the curl operator, which means that curl J is equal to 0. So this result grad 1 over r cross j is equal to curl j over r. Now, substituting for this result in the magnetic induction, then B is equal to mu naught over 4 pi times the integral over the source of the current, grad cross J over R integrated over the source volume. And again, recalling that the curl, this gradient operator, this grad operator, contains coordinates that are different than the volume, than the source of the current, then we can take it outside the integral. And according to this difference in coordinates, we can simplify this result by B is equal to gradient cross mu naught over 4 pi times the integral over the source of the current J over R d tau. That's by taking the gradient operator outside the integral. And this is simply equal, by the definition of the magnetic induction, this is equal to curl A. So curl this quantity is equal to curl A. That means this quantity, in parentheses, is simply the vector potential. Then we conclude that the vector potential A is equal to mu naught over 4 pi times the integral over the source of the current times the integral of J, the current density, over R integrated over the volume of the current. This is a formula where if we know the distribution of the current in space, we can evaluate the vector potential A from the distribution of the current in space. But we must recall that this value can be, or this integral can be rewritten in a different form if we have, instead of current density flowing in a volume, if we consider that the current is flowing in a wire, then we can replace the integral over the volume as current I, which is simply J times the cross-sectional area, and integrated over the length of the wire. And then we can rewrite A is equal to mu naught I over 4 pi times the integral over the wire carrying the current now, dl, which is an element of the wire, over R. This gives another formula for the vector potential by a wire carrying current I. And also, we must recall that the vector potential is not uniquely defined because we have this gauge transformation. We can add to it any gradient of a scalar function. The magnetic induction at a point in space thus can be calculated from a vector potential that is only if the vector potential is known in the region of that space. So we can apply the relation between the vector potential and the magnetic induction to evaluate the magnetic induction at any point in space. And at this point, I would like to end this lecture and thank you for your attention.